Hey, Michael, can you hear me now? All right. So I am dialed in over my cell phone, and I'm going to see if I can't prop it up on something on the desk. Can you still hear me if I put it like this? Okay. All right. Awesome. Michael, thanks for dinging in. I appreciate it. I'm sorry we had audio trouble. Okay, thanks. All right. Okay. All right. Oh, Kat, thank you. Yeah, there it is.
Well, yeah,
Oh, no, that's this.
Yeah, but you haven't, shared it. So while he can hear us, he cannot see us now. Okay, so, Are you recording still?
Yeah, it says it said it was.
Okay.
But let me go back and check, because.
Okay.
Yep, it went away. It was red a minute ago. No, it says stop recording. Okay, so it's recording. All right.
And then just open your laptop.
That's okay. Thank you. If you hadn't thought about it, we might not have slides shared. Okay. So for concept orientation, it's a very pragmatic and useful issue with terminology development, because if you are creating, for example, a valid value list or a pick list for a data element on a screen for something, the terms in that pick list should adhere to these three things. This is how sort of fundamental this is to a lot of stuff that we do in any type of data collection, not just in managing or developing control terminologies, but it also applies to those little bitty 4 or 5 term pick lists that you use. There are also two things that should not be a part of a control terminology, even a little pick list, and that's synonymy and polysemy. So synonymy is basically when two words mean the same thing. So we can have a synonym table, but not have two words meaning the same thing as a part of the terminology with two different codes. We good? Does that make sense? Okay. And then polysemy, meaning a word that has more than one meaning. So the example I think Semino gives in his paper is MI. So like if you put MI in there, is it like mitral insufficiency or is it myocardial infarction? So trying to stay away from things like this. So if you do the green things, doing the green things assures that you will never screw up and do the red things. So concept orientation is a very important part of terminology development, including pick lists on data entry screens and forms. So context and ambiguity are other issues that come about with control terminology and use of control terminology, and that's the fact that the context sort of creates some ambiguity. So, for example, if you have, if somebody comes into the ER and they're in for a rule-out myocardial infarction, and that's different than actually being there because they're having a myocardial infarction. And that is different yet again from a term of history of myocardial infarction in the record somewhere, or family history of a statement that says no myocardial infarction. Basically the only way to prevent that from happening, because in a controlled terminology, in the ones available today, you would not really be able to code for all of these things differently. And you wouldn't want to assign the term myocardial infarction to all of them, because all of these things really don't mean the same thing. It's not a level of granularity issue. They're just not the same concept. And so for the only way to fix that context-related ambiguity is to capture the context and to retain the context along with the word. So lecture before last, we talked about the list in Shortlift and Semino about the 5 things necessary for a data element. If you want to take a step further and think about things necessary to interpret a data value, context is often necessary for interpreting a data value. So So sort of with control terminology, being able to convey meaning goes a little beyond the terminology. Because of this issue, you also have to collect information, collect context about the data so that the data can be correctly interpreted. There's other context-independent types of ambiguity, and that's just different meanings. So the example Semino gives is MI, myocardial infarction, mitral insufficiency, medical informatics, whatever. It's ambiguous unless you specify. Concept permanence is another characteristic, or a desiderata, a necessary thing for a good terminology. And so basically concept permanence says that once you've created a concept, you can't change it in the terminology. So, for example, a while ago, maybe 10 years ago, the definition of high cholesterol changed. And so if you were going to code people before the change as having high cholesterol, hypercholesterolemia, then today you're going to code them as having hypercholesterolemia. Guess what? You're hosed, because those two things do not mean the same thing now, because there was an old definition and a new definition, and the level changed in the definition. So unless you don't care about the subtle differences in that definition, that use of that would violate concept permanence. So if there were an old term, if there were a term existing, say we were back 10 years ago, and I was managing the terminology, we all were, and the term changed, we would all come together and we would say, oh, okay, we need to retire the old term, label it as deprecated, label it with this time period, and after the new definition becomes final, have a new term and a new code that goes with it, so that people would know that the definition changed. Yes, ma'am?
So how did this play into the creation of the expansion of IDC 9 to IDC 10? Because you went from 10,000 to 64,000.
Yeah, so it wasn't really deprecated stuff. It was adding concepts. So like for the injury types, injury saw a big expansion. Miriam's looked at it more than I have. She might be able to rattle off the areas where it changed. But injury mechanisms, so like now there's some mechanism of injury in there, like hit by a bike while falling off a bus or something ridiculous.
He had their airway exploded. Children's was the benchmark for it.
Yeah.
They tapped up for the expansion of that area, and it is ridiculous. It's so granular. I mean, it's the minutia involved, and I wondered how this kind of impacted, because it almost seems like there's so many you can't tell if some are absorbed by others, or what is it, multiple parts?
Yeah, so anytime the definition would have changed, if they were adhering to the concept permanence, which ICD 9 or 10 might not, if they were adhering to concept permanence, they would have deprecated that concept. So that literally, that's what that means. Another characteristic of a good terminology is that you have to have a non-semantic concept identifier. This means like a meaningless code. So like those of us that give our files and our directories on the computer names that we know, like Tuesday's lecture, September 28th or whatever, okay, this says not to do that. That name carries semantics. So say if I had a medical record number, if I used for a medical record number, if I said that parents would be 00 and some random number -00 for parent, -01 for children or whatever, okay, that would be putting semantic meaning into that identifier. That should not happen. It's really bad, because you need to uniquely identifying terms in the terminology is completely separate than defining them or making them human readable or anything else. And in order to manage well the identifiers, it's best not to cloud them with trying to do anything else but just have a non-semantic concept identifier. So if you looked after Tuesday's lecture, if you looked on USHIC or on CADSR, the two big data element registries, you would see that each data element there has a concept unique identifier on it. Make sense? Okay. So we're going to spend a lot of time on this slide. So because in the this is really the only area where we're going to talk about graphs in here. There's a whole other class about graph and network analysis for those of you who are going to use it and need it. So I just decided to put it in here since Semino's paper covered it pretty well. So the concept of a graph is, look up there at the thing labeled undirected, okay, and look only at that. Don't look at the rest of them. That has two features. It has something called nodes, which are the little purple balls, blue balls, and the little thing between them called edges. Cat, that is not funny. So basically a graph has two things in it. It has nodes and edges. So when you think about parsing a graph or using a graph database, you're defining two things, nodes and edges. So when people display a network, like from social media, all the connections and stuff, they're displaying a graph. Has everybody got that? Okay, sorry for that base level explanation, but I want to make sure everybody had heard of it and was not thinking about X versus Y. So there are multiple types of graphs. One is based on whether the edges have a direction or not. So that's a directed versus an undirected graph. And literally the difference is the arrow. The arrow sort of signifies that in that relationship between those two nodes, there's some directionality in it. So that would be a directed graph. Other sort of variety of graphs are cyclic versus acyclic. A cyclic graph means it can connect back on itself, the nodes and edges, and form a loop. And an acyclic means that no loop can be formed with the graph. So two sort of different ways to differentiate types of graphs. Are we good on graphs? Okay. So remember those. Sometimes people talk about a DAG. It means a directed acyclic graph. And so when people are presenting stuff that's based on graph theory, they'll use these terms to describe what they've done. So it's important to understand them. Then we get into using graphs to depict issues of hierarchy. So when we say a taxonomy, we mean a strict hierarchy, like on here. So if we look at 1C, 1C would be a strict hierarchy. 1E would be a strict hierarchy. 1D would be a strict hierarchy. 1B would not, and 1A would not. So they're just fundamentally different between a strict hierarchy versus not. So when we say a strict hierarchy, we mean one tree, one backbone of the tree. And so what polyhierarchy means is that there's not just one backbone of the tree. Polyhierarchy gets you from a tree to a web. So, for example, if I had the term tuberculosis, I might want to say that tuberculosis is an infectious disease. I might also want to say that tuberculosis can occur in the lung, and it can occur on the skin, and it can occur in a bunch of other places. So for each of those places, I might want to be able to express that relationship. And so those would be different. The other thing is I might want to say that tuberculosis is caused by a mycobacterium or whatever the bug is called. I might want to say other things about tuberculosis. Each of those other things would represent a branch there in that hierarchy. Does that make sense? So you can have, for a lot of diseases, there are multiple ways that you might classify them. And the point is if you have a controlled terminology that's just a strict hierarchy, you can't do that. So it makes you have to use a polyhierarchical terminology in order to express all the relationships that one might want to express. Sorry, Michael, for the bang. Okay, so another issue is that terminology systems must have formal definitions. What Semino means by formal definition and what Dr. Brookhausen will mean by formal definition when he comes in is not words. He means computable logic or computable parsable symbols. So logic is one way to do that. There are other ways to do that, but by a formal definition, Semino means something explicit enough that can be programmed by a computer and be accurate every time. Another form of or issue with controlled terminologies is to reject not otherwise specified. The thing that we talked about concept permanence is in effect here. So in the old ICD, there was concept of not otherwise specified. So I don't know, if there was some cardiac issue and you didn't know enough to code it to one of the existing terms, you might just say cardiac issue not otherwise specified. Breathing difficulty not otherwise specified, whatever. The problem is that as science grows and more conditions get discovered and we understand more about mechanisms of disease, that concept is not otherwise specified changes over time, because the membership in the set of things that were previously coded to not otherwise specified before some new disease got discovered, and the ones that are coded to not otherwise specified after the disease got discovered, those are now two different populations. And that's a problem with respect to data use moving forward. So using not otherwise specified, although it's a lovely way to make sure that your codes are exhaustive over what you might want to express, it really bites you in the butt anytime the codes change and you add to it and something that was previously not otherwise specified is now specifiable. Make sense? So that's referred to as semantic drift in a controlled terminology set. Another issue with controlled terminologies is multiple granularities. So, for example, a primary care physician might just care about diabetes, whereas an endocrinologist might care about all sorts of different types of diabetes. Multiple granularities you usually find them in controlled terminologies. And basically, for one controlled terminology to meet multiple uses, it's really inevitable that you're going to have to represent multiple levels of granularity in a controlled terminology. So Semino added that in as one of the factors. The other requirement is multiple consistent views. So in other words, you can, if you have a big terminology, you can collapse fine-grained things into one. So look at 1A. Say if I just wanted to have the relationship between A to B and the relationship between A to C and collapse everything under it, that would be completely fine. That's legit and doable. You can hide intermediate classes in a representation. So if I wanted to take out in 1A, if I wanted to take out E, for example, I could do that and hide that. Or in 1C, they've taken out B, so it goes directly from A to D and A to E, and A to F. They've taken out B and C in that. So that's a legit thing to do, is to hide intermediate classes. This is for viewing the stuff in the terminology and for using it in computation. It's okay to restrict a user to a single branch of the tree. That's completely legit. We do that all the time. For example, if we're using ICD to code, but we only care about acute coronary disease, then we're going to restrict them to that part of the tree and the valid value sets they might be able to pick from. The warning that they give is if you look down at 1F. So the issue with this is that in the two different branches of the tree, if you look at the node E, if you look at one branch of the tree, it goes A to B, and then B has children D and E, and E has child G. But in the other branch, in the C branch, E has child H, but not child G. So that's inconsistent because E has a different parent and E has a different child in them. So just a warning that that the views, if you have multiple views, they all have to be consistent between the views, logically consistent between the views. And he talked some in the paper about representing context. We've talked about that before. This is just an example in representing context, for example, with ISM relationships in the top. So swelling is a pathologic function. Joint swelling is a finding. So an example of how you might represent context. So basically, control terminologies have to evolve gracefully. So when we go from ICD-9 to ICD-10, all of the previous issues that we've discussed in order, because some of the things, the desiderata, were adhered to in the development of ICD-9 and 10 that enabled the terminology to evolve gracefully where it could. There were other areas probably within not otherwise specified, for example, that where it would not have evolved gracefully. The reason why a terminology has to evolve gracefully is in something like medicine, the science and the terms are going to change. And so you have to be able to be rigorous enough in the representation in order to handle that change. Recognizing redundancy is another aspect of a good controlled terminology. And so, for example, synonymy is good. It allows people to use terms that they know as long as you've computationally handled it well, where the terminology itself is not redundancy. Your redundantness is in the synonym table for the terminology. It enables you to code. If you can code the same thing multiple ways, for example, the two different meanings, two the same meanings in there with two different codes, that would be an example of coding the same thing multiple ways. That's bad redundancy as opposed to good redundancy that enables you to code it to the same code but use the words that you know. And so the goal with a good terminology would be to provide a way to recognize redundancy and maybe render it transparent. A good example is in pre and post coordination. So, for example, if like SNOMED has pre and post coordinated terms in it. So if you had this term here, left lower lobe pneumonia, and then you had this here, that was, this would be pre-coordinated over here, it's all concatenated stuff together. This would be post-coordinated over here. So if you have a computational way to be able to recognize those, recognize the redundancy, that's what they mean by make it transparent and recognize the redundancy. So the reality is that we're going to have all sorts of multi-use problems until we can represent reality well. But we really can't represent reality exactly, so we're always going to have terminologies that are inadequate for some use that we might want to put them to. And why is that? What quote did we talk about previously that warned us that this might be the case? Yes, all models are wrong. Some models are useful. A terminology is a model of reality, an inaccurate one. So thus the concept versus realism. Well, I'm not going to go into the detail in here. Okay, so the ultimate success really is representing the real world such that it is computable. And some of us believe that data elements are a good way to do that, data elements in combination with controlled terminology. There are still people who don't believe that. That may turn out to be wrong one day. We don't know yet. It's an unanswered question. You can tell what I believe, right? I think it's the Holy Grail. I think we can add enough semantics behind data elements with things like the work that Dr. Bruckhausen does to make them easily used by humans and have the rich semantics that we desire. So data elements and controlled terminology, to link the discussion Tuesday to today, they actually work together. So earlier I talked about considering a pick list as a controlled terminology, a little bitty one. You can have a controlled terminology with 3 terms in it. You can have a controlled terminology. Kat said, ICD has 60-some thousand terms in it. So you can use the controlled terminology to code the question or the prompt, in this case, HCV status. So there's going to be a code for HCV. You may have a controlled terminology associated with some valid value list for the answer. Maybe it's a subset of ICD where you've restricted it down to just one little piece in the hierarchy. And you might have controlled terminology not just for the question or the prompt, the terms in the prompt for the data element or for the valid values for the responses. You might have controlled terminology for the data element concept itself. So, for example, in the case of lab tests, there's a controlled terminology called LOINC, logical names and observations or something. It's the lab terminology, observations and identifiers, codes. So LOINC would give you the code for the test itself, for the prompt. And then you might have another code for the concept of the disease about which you might be collecting information. So you can at times, depending on how expressive the controlled terminology is and whether there is one that covers what you need, you can attach controlled terminology at 3 different places on a data element, potentially. And then, so basically data elements with associated controlled terminology, there are people that believe that they sort of are the nexus in this model. And as we go through and talk about procedural knowledge, we'll come back to this. And when we talk about UML, you'll see it a little bit in the UML models. And so why do we care? Because individual information systems work just fine without any of this stuff. We care that when data are shared or combined, we might have a reason to have them coded the same way so that we can look across data sets. And examples of where we might want to do that are decision support or data warehousing or institutional reporting or even external reporting. For example, sending reportable conditions to the health department. So we can do nothing and map when we're needed. Like if all we care about sending the reportable condition to the health department, we can just map it on the way out to whatever standard data elements and control terminology the health department uses. Or we could code it up front and send it automatically when it goes. We could change to a monolith system. I had this slide at Duke, so we could use one big monolith system for everything and have institutional standardization, not worry about anybody outside. Today we can't do that, right, because of meaningful use and health information exchange. Or another possible solution is actually controlling our semantics and using standards that other institutions use so that we can exchange data with other institutions. Even though it costs quite a bit more up front, I think the tide is really turning towards controlling the semantics and using standards that everybody else is using. Some examples of how this might work, there's many different ways to do this. The way, for example, that the National Cancer Institute does it is there's a metadata registry where the data elements are stored. ISO 11179 is the standard that specifies how that's structured. And then there's a separate vocabulary server where the controlled terminologies are stored. And it seems it's on the surface, it seems simple, right? Like ICD, it's just a file, right? Just put it out there and use it as a lookup table. Okay, that is not the case. Those things are updated, they're changed. What about the synonym table? What about changes you might want to add to the synonym table for local language to better the coding? All of those things about managing a controlled terminology set within an institution are handled by softwares called vocabulary servers. So the NCI, for example, Enterprise Vocabulary Services, or EVS, is their vocabulary server, and their metadata registry is CADSR, which you guys, we talked about in the previous lecture. And so how that might work in an architecture, this is something that we were working on at my previous institution, planning on instituting a metadata registry and a vocabulary server. This was before they implemented EPIC, where there was a form analyst that built individual forms within the system. So the idea was that the form analyst would go to the metadata registry, get the standard data elements instead of making new ones on each form, which they were currently doing at the time. Unfortunately, they came back and told us that they had so many forms to build in the backlog, there was no way they could take the time to look the data elements up in the registry, and they didn't care whether they used data elements, different ones, made new ones. So that's reality. So this is a real architecture. So that's the reality of it. But so the form analyst would look in the registry that we wanted. They would build the form. The forms would be in the EHR, and then when the clinician up top went to get the data information out, they would go to the self-service query tool on the warehouse, pull the information out, and because people had simply use the same data element, the standard data elements on the forms, that data would be together and they would be able to do that well. Epic fixes a lot of this in some ways. In other ways it doesn't, because you can add new data elements in Epic and you can hose yourself very easily in there. If you have strict information governance within your institution, you can use Epic successfully in exactly this way. So it depends really institutionally how you're going to use it, whether it's a monolith or whether it's an architecture like this that we have built out. So in summary, so far we've talked about data elements, the ISO 11179 standard, and control terminology and how they work together. I did post the references in the reading for you. So you're not responsible for any detail in the references beyond that which is in the slides. There is a whole class worth of information posted out there in the reading. As far as the level of detail and the extent of the information, please do not drive yourself crazy with it. Okay, that's that one. So now I'm going to talk about unified modeling language. So your lab for the week is going to be to pick a topic area that you like, whatever it is that you're interested in, maybe for your thesis or your dissertation or something that you're doing at work. It could be something you're already working on. I don't care. I just care that if you don't already know the UML diagram types, that you get a chance to play with them. I don't care that they're completely correct. I care that your brain thinks through them, and that later on in your career, when somebody says, oh, I'm designing a system and I need to do the activity diagram, that you can actively engage with them and you at least know what they're talking about. So we're basically going to talk very high level about the purpose and the notation of the following UML diagrams. Why is it automatically advancing? Which are the use case diagram, the class diagram, the activity diagram, and the state diagram. So basically, at the end of this, you should just be able to understand or describe what each type of diagram represents, and what the symbols and the conventions are for making the diagram, and be able to read the diagrams and create a simple one. A lot of people get wrapped around the axle with wanting to make sure their model is completely exactly correct before they let other people see it. It's really not important. The most important thing is to get something, a straw man, down on paper when you're trying to design a system or work with a group of people to understand requirements for a system, because chances are your first guess of what it's going to be is so wrong anyway, you're going to redo the whole thing after that first meeting with them. So it's most important to get something down on paper. I usually start on a whiteboard. Kat has witnessed this. And Miriam has witnessed it. It's more important just to get the base concepts down. Okay, so remember harken back to the first week when we looked at this diagram and we said that in informatics it's about several things all wrapped up into one. It's about information flow and it's about process flow together. And it's about the content that is involved in those transactions. And so what UML does is, in the past, there were older representations. So ISO 5807, I'm taking Michael with me. 5807 is an old information processing standard. It's the original source of the flowchart symbols, as far as I can tell. Then there's Jordan Code, Gaines Sarson. They're probably in the 70s, 80s attempts at being able to model requirements for information systems. And they're really the precursors in a lot of ways to what's known today as the Unified Modeling Language Standard, or UML. And there are also entity resolution diagrams, or entity relationship diagrams, that people use to represent the referential integrity in relational databases and the concepts of the tables. We'll do some of that when we hit relational theory. These are sort of similar to one of the diagrams that we're going to see in UML. So UML was the red was sort of born out of the application, the requirements analysis, and sort of the application development community's experience with different representing requirements for systems. And so there's a lot of things that one might want to represent, like the context in which the system is going to operate. So for a lab system, the context will be that the system operates within the hospital lab, and it might have to interface with the electronic medical record, and it might have to interface with the scheduling system for admission, discharge, transfer, and it might have to interface with some external reporting stuff. That's what I mean by context. I mean what the system has to operate with, interface with, that's outside of the system itself. Process steps or workflow is another thing that we might want to represent with the system. Some systems are just information capture, and so there's really not a lot of workflow in them. Some systems are all workflow, like a document control system that worries about what's the final version, what's the draft version, who reviews it now, who has to review it next, and managing the flow of all those documents through an approval process. The real content of that system is wrapped up in the text document, so the system has not much data element content aside from metadata about documents. So the main thrust of that system is a workflow system. In clinical care, there's just as much workflow as there is data, and sometimes people forget one in favor of the other. In the biomedical sciences, it really depends on what type of system it is and whether it's for just research or whether it's more of a production grade system. The more you get into production grade systems, the more you get into more intense workflow, the more you stay down in research systems. In general, the more you're emphasizing information content over workflow. There's data transformations that might need to be represented. For example, how you're processing data. Are you checking it for errors? Are you correcting the errors? Are you coding the data? Are you doing text processing and extracting out structured text, whatever? Those are what I mean by data transformations. Flow control and state. This is a workflow-oriented concept. If it's within a computer program, you think of flow control as the logic. In a process, flow control is the logic that controls the steps in the process. And then the roles involved, the user community. So all of those are things that we might want to represent as an informaticist when we are designing a system and we're working with a group of people to design a system. So the background on UML is that it stands for Unified Modeling Language, and it was developed by the Object Management Group. It's still maintained by them, and it was really created to overcome the differences in notation for all those different models in that table that we saw. And then it also it incorporates a lot of the notation from those older mechanisms. And the other thing is the IT community really tried to move the science forward by being able to specify enough in those models to have model-driven architecture and model-driven code to where there's enough specificity in the model itself to develop the code and the system from the model. In my old institution, we actually had a system that did that parsed UML diagrams and built computer systems from the expensive level of explicitness in the models themselves. In informatics and business analysis, we don't tend to specify things at that level of detail. We're not intending usually our diagrams to be used to generate code and build systems. We just want to communicate very explicitly what the requirements for the system are. So we're not going to be doing any model-driven coding here, although it is kind of fun. So the types of diagrams that we're going to talk about, there's sort of three different types of diagrams in UML. One is structured diagrams, and they represent what's called the static aspects of the system. And so that's stuff that's not stuff the system does, it's content of the system. Then there's behavior diagrams, which represent the dynamic aspects of the system. So this means stuff that changes. For example, workflow in a system, the steps, how information moves and changes throughout the system. Those all would be considered dynamic aspects of the system. People tend to call those behavior diagrams rather than structure diagrams. And then there are interaction diagrams, which are basically very detailed behavior diagrams. Since we're not using this to build code, I've never used these diagrams in anything that I've ever specified in my career. Maybe my specs have been grossly inadequate. We're all learning. I might learn that one day, but I've never used these. So we're just going to go over the first two. The first one that we're going to do is a use case diagram. Somebody actually turned one of these in. I'll leave it up to you to identify yourself as a conceptual diagram. And I'm like, wow, that really is a conceptual diagram. That's awesome. And so a use case diagram looks like this. And so what a use case diagram shows is it shows the roles and what functions the roles need to do in the system. So the roles are the stick figures. So here we've got a clinician and a pharmacist. I guess this is maybe e-prescribing or prescribing with a pharmacy. And so the three functions, according to this, that the clinician needs to be able to do is list out meds that are prescribed. They need to be able to document a dose, frequency, and a route, and they need to be able to print a prescription. No warranties as to whether that's appropriate stuff for them to do or not, but that, according to the diagram. And the pharmacist role has two functions according to this diagram that they do, and that's print a prescription and document that a prescription's been filled or picked up. So that is a use case diagram. So use cases are meant to describe interactions between users and computer systems. They basically capture what user visible functions there are in the computer system. So what a user sees and is able to do when they see the screen. They're typically used during analysis and design in order to scope a project. So if somebody's going to build a system, the first thing they're going to want to know is, what do you need the system to do? The best way to tell them is, I have these 4 types of users, and these 4 types of users need to do these things. And that's what a use case diagram does. Now, as you might guess, so this is just showing the actors. A use case diagram is pretty high level, like just the bubbles and the stick figures. It's not a lot to write code based off of. But remember that in the UML standard, one diagram does not stand alone. It stands with all the rest of the other diagrams together as a set of specifications. And so with the use case diagram is a use case report. In HL7, we call these storyboards. And so these would be actual stories of how people use the system. So for us, it will be Peter, patient, shows up at the doctor, and this happens, and then this and this and this happens. And then Peter has to go to the emergency room where they have to schedule him for the OR. The whole litany of a picture, a snapshot, a scenario of a user's interaction with the system. All that would be in the use case report, and you would put these kind of things in there. The preconditions, whatever had to be happened before the scenario started, the flow of events. You want use cases for main alternate flows. So say the OR is full and Peter has to wait. Okay, that would be one of those alternate flows. What happens afterwards, how it sort of closes out, and any special requirements. And then the use case reports or the storyboards then refer to the diagrams and also any mock-up pictures of the user interface if it's specifications for a system. So that's use case, diagram, and report. So literally, it's that, when you're going to make your use case for your lab, if you're, like, say you're going to make a system for Meredith to do online shopping to buy some shoes. So there's going to be a Meredith stick figure, and there's going to be a bubble that says, pick out shoes, view shoes, buy shoes, pay for shoes. And then there's going to be another bubble that says online merchant. A stick figure, and that online merchant's going to have some functions like see Meredith's order, fill Meredith's order, and ship Meredith's order, and collect money for Meredith's order. So that is an example of what a use case diagram would be for a simple scenario. Does that make sense? Okay. A class diagram is like, I call this the business end because I'm a data person. The class diagram shows the data that's in the system. Okay, you're not supposed to be able to read this. There are examples of these. I put special examples in Blackboard for you. So in a class diagram, I tend to do it topically based. So like if I was going to have data for a primary care encounter, I might have a patient table with patient demographics in it. I might have a table for encounter information, like the date of the encounter, the facility, the provider assigned to the encounter, the main diagnosis on the encounter, or an identifier for the bill that was generated based on the encounter. And then I might have a vital sign table, and then I might have a lab table. And so those will correspond to boxes in the class diagram, the way that we use them in HL7. A class in the UML modeling language can be used very differently and can have more than, these classes have 2 parts. There's other parts on the classes that correspond to different stuff in UML, the behaviors of the class. So, for example, if a class is a piece of code that goes out and gets some piece of data and brings it back and processes it, that behavior will be specified. We are not going to talk about using these for that because we don't really go into that level of detail in UML. So we're just using it to describe what class of information and what attributes. So when we do them for HL7, we list the data elements. Those red things listed in the boxes will be the data elements in the class. So in the vital signs class, I might have test and test results, where the test will be the test name, like systolic blood pressure, diastolic blood pressure, and the result will be the numerical result that I might measure. Maybe I might have another attribute in there that might say units. Or I could have a data element that says systolic blood pressure and a data element that says diastolic, depending on how I might structure it. Either way you want to structure it for yours is fine. If you just want to list the concepts for now, that's fine. You'll learn more about different ways to list the concepts when we talk about relational theory. So this is an example of a class diagram. You'll notice that it has boxes on it. It has associations, which are the lines, and it has cardinality and modality, which basically are counts of things. Like a patient can have 0 to many encounters or 1 to many. The star means many. Or within an encounter, there can be 0 to 1 claims for that counter, a bill produced for that encounter. So this is a really simplified example of a class diagram. So in the patient class, I'm basically saying that a claim is associated with one patient, and the differences in the arrows on the lines actually have meaning. So the arrowhead, the triangle arrowhead, means generalization, specialization, meaning that a interventional procedure and a diagnostic procedure are both types of the generalized procedure. And the way that the UML modeling works is that stuff that applies to both the interventional and the diagnostic procedures would be listed up in the procedure class. Only the stuff that's specific for the interventional procedure would be in the interventional procedure box. And only the stuff that's specific for the diagnostic procedure would be in the diagnostic procedure box. Because of the generalization or gen-spec relationship, generalization, specialization, because of that relationship, the children of that relationship inherit the other things from procedure. So if a procedure has a date and it has a location and it has a patient and it has a provider, that would apply to both interventional and diagnostic procedures. So I would put those things up in the procedure box. And for interventional procedure, I might have interventional procedure type or something specific to interventional procedures, like I might be expecting an outcome or something. Then in diagnostic procedure, I might have something else there, like maybe if they're going to render a diagnosis on the basis of the procedure, I might have that there. Whereas in interventional procedure, I wouldn't have a diagnosis made on the basis of a procedure. So the stuff in each box should be the stuff that pertains to only that box. The stuff in the higher level boxes, like the procedure box, should be the stuff that applies to the boxes beneath it in a generalization-specialization relationship. Does that make sense? Okay. So the other types of relationships are two. These diamonds, one is simple aggregation. It means just like a bag. Like when I give my 2-year-old a bag, she walks around the house and she puts all sorts of stuff in it. Okay, that's simple aggregation. It's the stuff in the bag, whatever it is I put in there. The composition is a little different. It means that that a claim is composed of these things, these parts. So it has a little different meaning between those two types of relationships. For the stuff that you do, if you recognize any of those relationships, that's great. If you just want to use simple associations without specifying the type of association, that is completely fine. Make sense? So this is up close how one looks with some of the generalizations, specializations. So like this box here is test. The one up top is the test, and then the one down below it is the tuberculosis culture. This is all of these. The examples are in Blackboard for you, just so that when you do one, you can look at an example of one to follow. And this just says what I said earlier, that the behavioral parts of the class we don't use. So for your classes, your box just needs to have two parts. If you have something like you do this for a living and you have a diagram that you've used before and it has the other parts, don't delete them, put them in, it's fine. But you don't have to do the other parts of the box. The next type of diagram is going to make more sense to people, I think. It's a flow diagram. It's basically just a flow chart. And we'll talk really specifically about, because for one of the goals for this class is that you can do an accurate flow diagram. So we're going to cover how to do these in great detail in the procedural knowledge lecture. For now, I just want you to get the basics of the diagram. The UML activity diagram, like a flow chart, shows movement. It does use fewer symbols than the standard flow chart symbols, but that's okay. It works, and it's what the UML standard says. So the box with the rounded sides is an activity. Motion and direction are shown by, or flow, are shown by an arrow. A decision or a logic branch in a process. For example, when I wake up in the morning, I can either go brush my teeth or I can go eat breakfast. And so that's a decision. So if I was going to diagram how I get up in the morning, and there is like a popular example of a flow chart on the web that does that, then I would put a branch there where I make that decision of whether I go brush my teeth or whether I go get something to eat. And then you have a process start, which is the solid black ball, and then a terminal symbol, or process end, which is the black ball with the ring around it. So a really simple example, we might have a scheduling appointment. So a patient might call the office, is where the process starts. Then a receptionist might answer. The appointment is scheduled or not, based on the results of that call. Then after the appointment is scheduled, then either an office visit occurs or the patient doesn't show up, and then the process ends from there. So really just simple, literally sequence and flow control of steps. So here I used, there's two symbols for branch. I used the line for branch rather than the diamond. You can use either. They're equally valid in a UML activity diagram. The last one that I'm going to talk about is a state diagram. This is probably the most confusing for people. It basically shows the different statuses that something can have as it moves through a workflow. So there's rectangles and there's lines. So from a construction point of view, this is the simplest diagram because there's only two symbols. From an understanding point of view, let's think back to that activity diagram that we talked about scheduling a patient visit. So a slot on a calendar in an office might start with a schedule of open. Then from open, it can either go to a status of scheduled or tentative on a calendar. If it's scheduled, it can go to three places. The patient can either miss it, the patient can cancel it, or it can go to a status of arrived. And from arrived, it can only have one status, complete. Now, I'm not saying this is an accurate state diagram. This is an example state diagram. Okay, so does that kind of make sense how the So when we saw the flow, this says the task that people do. I do this, and I do this, and I answer the phone, then I schedule the appointment, then whatever. This shows if I'm an appointment in an information system, what happens to me. Have you ever, when you were little, seen that TV thing, I'm a bill on Capitol Hill? Okay, and it shows the state diagram of a bill. If we had time in here, I'd play that, and we'd diagram out the state diagram of the bill because it'd be kind of fun. But that goes through the different statuses that a bill can have as it gets made into law or whatever happens to bills. So that's a state diagram. So for the lab, again, this is a formative lab. I want you to pick some small example. So Hoda, if you're doing labs, you might pick what happens to a sample when it comes into pathology. Felicia, you might want to do what happens when you have to go give a respiratory therapy. When somebody calls up and says, we need a nebulizer in this room. And, pick something little teeny. It'll grow like a pot of soup, and it'll be much more complex than you ever wanted it to be. If you want to pick waking up in the morning, that's fine. I'm not sure what the state diagram would look like, but if you have one in your head that you think could be used, that is completely fine. Literally, I just want you to go into PowerPoint, no fancy modeling tools. It would take you an hour just to figure out how to open a diagram in Enterprise Architect. It did me. And Rational Rows, another modeling tool none of us can afford. So I want you to go into PowerPoint, and I want you to draw these models. Okay, no fan. Okay, if you do this as a profession, sure, I was looking at me like you gotta be kidding me. It's okay. If you do this as a profession and you want to turn in something from a modeling tool, then just PDF the different diagrams and turn them in. It's completely fine. So if you already use a modeling tool, that's great. That's lovely. For the rest of us, the concepts here they're considered important across all of the tracks in the program, that you can take a diagram set and be able to understand what somebody's trying to communicate, and that you can engage with a technologist in making some specs. Maybe in this way, this is one option for you to do that. And so for your first one, we just want you to go into PowerPoint. I'm going to show you some things in PowerPoint. So I'm going to make this a blank slide. So here are the shapes in PowerPoint. Here's a rectangle. I'm going to put that here. All right, I didn't click on it. Okay. Now, because I'm fanatical about not liking color unless it has some massive meaning, I'm going to make this a black and white box. And then let's say I need a decision. So I might go down here to flow chart shapes, and I might find me a decision box. Not that big. Okay, and then I'm going to make it the same format because I'm kind of fanatical about that. And then I'm going to go get me a line. And these shapes have connectors on them. When you hover over them, the red thing's the connector, and there it connects to that one. You know why we like to use connectors? Because of that. So when you move the shapes and redo the diagrams, the connector's fine. The other thing that you need to know how to do is aligning these suckers to make it all neat and professional. No crooked lines. You got it? That's how. So literally, just do them in PowerPoint. It's the easiest thing. I don't care about beautifulness. So for your lab, when you're in the turn-in place, if it won't let you turn in a PowerPoint, just PDF it. If it lets you turn in PowerPoint, that's completely fine. So that is the lab thing. Any questions about that?
Is it a specific type of report? Do you pick one report?
All four. All four. So pick something that has some information content and some flow. So that's going to exercise your knowledge of what you've learned too. So it has to have some workflow involved, and it has to have some data content. I don't care if the data content's only 5 data elements or the workflow is only 5 steps. That's fine. That's completely fine. If the workflow is 20 steps, pick only a piece of it. Only do a little piece of it. We don't want big. This should not take you more than 4 hours. Okay, so 30 minutes of diagram, time management. You guys good? Okay, I think for quizzes, we had talked earlier about timing of stuff. I'm finding myself not wanting to post quiz questions until we've had the lecture, so that I can make sure that we actually covered a topic before I put, I don't want to put a question there that we hadn't covered, thinking I was going to get to it or whatever. So if you guys are okay, I would rather just, along with the lab, I would rather make the quizzes do the Sunday following. Is that going to screw? I hate to make changes during the class, but I'm finding myself giving you guys littler amount of time to do the quizzes and then having to move them back to give you guys more time. So can everybody be okay with that?
And I think when you look at it, it's still the same on Saturday, and discussion questions.
It's just a different week.
It's going to be wrapping our brains around the fact that 2 of the 3 are a week without time.
Yeah.
But other than that,
if you want to make the discussion question, if you want to just make them all due on that Sunday, I'd be fine with that.
So this is all of our comments are due a week after.
Yep, not the Sunday at the end of the week, but the Sunday at the end of the week following. That'll be easier. That'd be easier? Okay.
I think sometimes we'll have less questions and you'll spend less time.
Yeah, well, and I'm cognizant it's hard for me to wrap my head around, and so I'm sure it's hard for you guys to manage. It's not the intent. The intent is to make it as easy as possible, because I want you to think about the work and the content, not about the scheduling.
Well, that's what I'm saying. That's what I don't know.
Yeah. So if you guys if anybody needs to be late with something, let me know. I mean, we're not teaching this class to teach y'all a lesson in how to work and make sure everything's in on time. Not everybody thinks the same as me. Other people think it's a critical lesson to learn. I just want you to think about the work, and if you need to be late, that's fine. Let me know you need to be late. A few people have had issues. Email me. It's completely fine. That happens every day in the workplace. So just let me know. And so we'll do everything due on Sunday, the week following. Okay, so we have a question from Kat.
It's about the week 5 quiz, because I was reading
okay.
The thing that you had updated about the change in points for the question.
Oh, yes.
And then you had.
Thank you for asking.
A question that was marked incorrect, but so it wasn't the existing data quality question. Is that the one that had the incorrect?
No, the incorrect answer was the one about natural language processing. I picked the wrong one. When I went through and selected the correct answer, you click and I clicked the wrong one. And so basically I gave everybody credit for that as if you had gotten it right. Because if you read the quiz and you're like, well, shoot, the feedback says that was the right answer, and then you knew that you would have had to have selected another one to get it right. So either way, it was because I selected the wrong answer, it probably hosed everybody. So I just gave everybody credit for that. In addition, I had 12 questions on that quiz, and the questions were set at 10 points apiece, which made 120 points. So I went back and changed it from 12 to 10 points per question. I mean,
8.33.
yes, thank you. I went back and changed it to the right number so it would add up to 100 points on there. So you saw 2 changes, and I get that it was confusing as hell. And then some of the changes didn't take. Somebody emailed me and says, Meredith, it's still not right on mine. So it should be correct now. If your grade for the week 5 quiz is still not correct, I've gone manually through all of them twice now. But if yours is still wrong, please let me know.
No.
Thank you, Kat, for bringing that up. And the discussion forum question for the week is basically to post I'm going to make you put a stick in the sand about your class project. We're about midway through the class. So the discussion forum, I need you to make a decision about that class project because it is going to take you a little bit of time to do, and I want you to have enough time to work on it. If you put a stick in the sand and you hate the stick in the sand and you want to change the week before and redo everything the week before, that's fine with me. But I need you to tell me now what you're going to do class project on. And then, so if you want to change, you can change. I'll leave the discussion forum up. You can go back and update your post. That's completely fine and change it.
Yeah, the keeping out of the quiz issues, did they figure that out?
Yes, so they did figure it out. The Blackboard people emailed, and thank you again for that, Kat. The Blackboard people emailed me and Tremaine back. There's an option among the 30 or so options I can check for any given quiz in Blackboard, and it says forced completion, which means that if a student has internet trouble or the internet abruptly disconnects, it forces the completion and it saves the student's work. And so midway through for this last quiz, I checked that, not realizing, oh, I had been checking that before, or maybe there was I wonder what this does. So now we know what it does. If you have even the slightest jolt in your internet connectivity, it kicks you out. So I will not be collecting that anymore. Evidently, Blackboard is programmed so that it's fairly fault tolerant for jitters in internet connectivity, and it kind of keeps you, it maintains a lovely user experience in the midst of some of those jolts of internet connectivity. And so I'm going to allow Blackboard to do its thing, and if you do have a catastrophic failure, one time my cat puked on a modem, and the whole thing just spun down. It was fabulous. If you do have a catastrophic failure like that, not that anybody's using the modem properly, but you will lose your work on the quiz. Yeah. But it's better than every time. I think 5 of you got kicked out. Yeah. It was a lot of people. So it's better than that happening. So if you have a catastrophic failure, sorry, you have to take the quiz again. Other than that, I will never check that box again in Blackboard. And I promise I will tell other people who are using Blackboard this extensively in this program about all the wonderful things that I am learning and that you guys are having to experience. Okay, anything else, guys? All right, all y'all have a good afternoon. Next time that I have to record the class, I will post an announcement. I will email all of the students, and I will say something on the recording. So 3 channels. All right, thanks, guys. Hang on, I'm doing it now. Hang on. It takes me a minute because I can't see half the stuff I'm doing. Okay. All right. Recording stopped. And